Greetings. The root test for infinite series is related to the ratio test for infinite series in the way that it has very similar results from the conclusions that it draws. So we can consider some example. Let's say, and instead of n equals 1, I'll just write 1 here, going to infinity, just to write it quicker. The argument will be, let's say, 3 to the n over n squared. And I want to see, does this diverge or does this converge? And I can use the root test for this. And the root test is as follows. One takes the limit. I'll write limit n goes to infinity here, but next I'll just be writing limit to just write it faster. Although I'll still be meaning this argument is there. Limit of the absolute value of the argument here is this, but the nth root taken of it. So basically, we take the argument of the infinite series that we want to see is it convergent or divergent, and then we take the nth root of it. And first of all, we put it in an absolute value, and of all that we take the nth root. And there's properties for the nth root and the absolute value like this. It can actually go inside the absolute value, like if the absolute value wasn't there, we can just put the nth root then inside the numerator and the denominator, so actually the algebra won't be as bad as it might seem. And after solving this limit, we can actually get some result. So the result of this, let's say, in general will be L, and if L is larger than 1, then it's divergent. If L is smaller than 1, it's convergent, and L equals 1 is indeterminate. It's just, we don't have a conclusive decision. So we can determine straight away if an infinite series is divergent or convergent based on the result of this root test, as long as the value is higher than 1 or strictly lower than 1. Strictly higher or strictly lower than 1. If it's exactly 1, then we have an issue. And by the way, in the case that it is lower than 1, it's not only convergent, it's absolutely convergent. That means even if we take the absolute value for the argument of the infinite series, so even if the argument is put into an absolute value, the series is still converging. So that is the meaning of absolute convergence. So actually for L below 1, once again, for L below 1, it will be absolutely convergent. Alright, so we'll see how this one goes. So if you want to see, does this converge or diverge, we can use this very formula here. Well, in general, this is already that example, but in general, basically we put the an here. So that is the general case, and now we'll do it with this example to see. So this is one of the faster tests, as long as the algebra with the rooting doesn't take too much time. So we take the nth root of the absolute value of the argument, and what that gives, and I'll just keep writing the way that's faster without the argument, although I still mean it goes to infinity. Well, we have absolute value, the nth root of 3 to the n, so this will actually cancel out these two things. And it will be over the nth root of n squared. So what it is, basically limit of 3 over n to the 2 over n. That's algebraic manipulation here, how we can rewrite this root expression, this radical expression. And then what we have in the end is still approaching infinity, and approaching infinity meant by this. Well, if this approaches infinity, this goes to 0, and so n to 0 is 1. So it's going to be 3 over 1. I don't have to do absolute value anymore because it's positive anyway. So the result is 3. And 3, because it is higher than 1, then in this example, it means that it will diverge. And we can do a similar thing. We can take another example, and let's, for example, only change a little bit about this one. So n squared over 3 to the n, see how that goes. So again, we can apply the thing. I change the argument to a new one, and we'll try it out. I would expect now for it to be below 1 and therefore converge. So, absolute value of the nth root of the absolute value of this, and that will be basically this. I can just divide the exponents by n, and so we get this will be 1 and in total 1/3. So in this case it is below 1 and is convergent, and actually it's absolutely convergent. So even if absolute value was around the argument of the infinite series, still it would converge. So that's another example. Then we can also take yet another example. Let's say we have some not very nice polynomial expression. So we can, for example, take 3n cubed plus 2n over 5n cubed plus 5 plus n squared. And now this is the whole argument, and we want to do the and it's all to the n. I want to see what does that, how does that play out? Well, we take the same limit. We want to see does it converge or does it diverge, depending on the value of the limit's evaluation. So we put it into the absolute value. The nth root of that is taken, and this is actually gonna be exactly one of the cases in which this is very practical, because what we can very quickly get here is, especially if we have even like a complicated polynomial, but if there's an n above all of it, it will simplify actually paradoxically everything a bit. Well, n and n are cancelled. In this case, it is very useful. So we take the nth root of this, then we get left with the rational expression itself. There's two polynomials dividing each other, and now we can either take the argument of the dominant terms, or we can isolate an n cubed to show it more explicitly why the limit ends up being the way it is, the result. Let's say it like this, over n cubed times 5 plus 5 over n cubed plus 1 over n. So that's that. And now by properties of limits, one puts limits for both of these parentheses individually as well. This part gets basically cancelled out. Constants are not changed by the limits, but these things all will become 0 by the limit. So what is left is 3 over 5. So now it is below 1, again in this case, so it will actually converge in this case. It will only take a slight change in the coefficients here, and suddenly we could make it a divergent one. Maybe if I just switch these two. Alright, so those are some examples for the root test. In general, the point of it is to identify a good argument that could be easily used with it, and then one takes that argument, puts it into an absolute value, takes the nth root of all that, and takes the limit as it approaches infinity. The very same variable that relates to the argument that's inside the argument, we'll also put that variable inside the value of the root, and both will go into infinity, so it will be basically the infinite root of what is the argument inside, and then depending on what we get, what value we get, we can draw a conclusion.